Welcome to our colloquium. I'm speaking today with Paul Lasky. This is a joint talk. I'm Eric Thrane. We're both senior lecturers in the School of Physics and Astronomy and members of the LIGO Scientific Collaboration. And today we're going to tell you about GW170817, which was the first observation of gravitational waves from a binary neutron star, Inspiral. This talk is geared for physicists. So it will be fairly high level, but I'll take this opportunity to advertise that tomorrow at 6 p.m. we'll be giving a public lecture, which will be a little bit more introductory, and you're welcome to attend that as well if you're interested. So without further ado, I'll begin. So the field of gravitational wave astronomy began in earnest as an observational field 2 years ago with the first discovery of gravitational waves. And our first discovery were gravitational waves from a binary black hole. And this binary black hole event is GW170914. It was a huge event. It was a culmination of 100 years from the prediction of gravitational waves in Einstein's theory of general relativity at the beginning of the 20th century, through the realization that gravitational waves, ripples in the fabric of space-time, are a physical effect that can be measured, the development of detectors to measure these waves, and eventually their discovery by advanced LIGO. The event 150914 was additionally remarkable because the two black holes involved in the coalescence were unlike other black holes we'd seen before. They each had a mass of about 30 times the mass of our own sun, and this made them heavier than the black holes that we see in our own galaxy. So it was the beginning of the field of gravitational wave astronomy. It was the discovery of a new class of stellar mass black holes. And since then, we've had a busy first 2 years of advanced LIGO. We subsequently announced the detection of a total of 4 stellar mass black holes. And just a few weeks ago, some of our founding figures were awarded the Nobel Prize in physics for their work facilitating the development of advanced LIGO. And these are Ray Weiss, Barry Barish, and Kip Thorne. So here is a slide summarizing the published gravitational wave detections going into and through the first part of August of this year, just before the story that I'm going to tell you today really begins. And so we'll begin at the top of this slide. This is a sky map showing you the localization areas on the sky where we were able to determine, using LIGO and our partner Virgo data, where these gravitational waves were coming from. And our first event, 150914, is here. This was our first detection. We subsequently detected LVT 151012, which was a silver-plated or unconfirmed candidate event, but which most people in the gravitational wave community believe is real. Then there's 151226, which was the so-called Boxing Day event. This one had lower mass black holes, therefore lasted longer, and we were able to see evidence of precession. And then came 170104 up here. This one was notable for the properties we observed with black hole spin, but we stopped giving them nicknames at this point. And then finally, 170814, which is right in the middle of August. This was our most recent published binary black hole discovery. And this one is noteworthy because the sky localization area is so small. So if you take a look at all of the other allowed regions on the sky, they all take up hundreds or over 1,000 square degrees. And this is because all of them until 170814 involved two detectors, the two LIGO detectors, and most of our ability to localize the event on the sky comes from the time delay between the arrival time for gravitational waves at these two detectors. 170814 is special because, as you can see in the bottom plot, we were able to observe it not just with the Hanford Observatory in the northwest of the United States, the Livingston Observatory in Louisiana, but also the Virgo detector in Italy had come online. And we were able to see this black hole in 3 detectors. And this allows you to triangulate the position much more precisely. And so we were able to know where on the sky it was to within 60 square degrees, which is quite a dramatic improvement. At the time, we hailed this as a remarkable discovery because it would allow us someday, we didn't know when, to be able to provide astronomers with a very accurate or relatively accurate sky map they could use to point their telescopes and look for an electromagnetic companion, an electromagnetic counterpart to the gravitational wave signal. Black holes, of course, are not expected in most models to produce electromagnetic counterparts when they merge. And so while our astronomer colleagues had been looking for electromagnetic counterparts associated with these binary black hole events, none had been observed, and there was not a strong belief that we would necessarily see one. It would have been a bit of a surprise if we had. So the stage was set. We had discovered gravitational waves, we observed several binary black hole events, and we demonstrated the ability to pinpoint fairly precisely on the sky where the event was coming from. We were getting close to the end of our second observing run. It had begun at the end of 2016, and we were scheduled to turn off just in a week or two after we saw that triple coincidence event on August 25th, 2017. It was a nice run. We accumulated 117 simultaneous days of at least 2 detector data. We always need to have 2 detectors in order to be able to have a confirmed gravitational wave event. And we achieved a sensitivity which was roughly comparable to the sensitivity achieved in our first observing run, slightly better at times, but roughly comparable. And then, with just a week or so left before the end of the run, something special happened at 10:41 p.m. in Melbourne time. And there seems to be something with the start and ends of LIGO runs that seems to trigger interesting events. So maybe we should just constantly be turning it on and off. That day, I had arrived at Mount Beauty for a family snow holiday, my first Australian snow. And so I went to sleep a little bit early and woke up to this. My phone was beeping off the hook. My inbox was completely saturated. And my co-presenter, Paul Lasky, had texted me this. Oh, it's a little bit difficult to read, but I'll read it for you. I know you're on holiday, but I think you'll want to hear this. BNS stands for binary neutron star with Hanford-Livingston signal-to-noise ratio of 30, coincident short gamma ray burst, an interesting high-energy neutrino that overlaps with sky localization, but is 155 seconds before the gravitational wave trigger. So the 2 things you can take away from this are that, first of all, gravitational wave astronomers speak a language other than English, which mostly consists of just acronyms. But moreover, on the very morning after the event, it was clear that there was something amazing had happened. A binary neutron star coalescence, coincident with a gamma ray burst, and with a huge signal-to-noise ratio. I wrote back, amazing. And I didn't include all of the conversation, but I went on to say that of all of these things, any one of these was, a completely amazing, remarkable thing. But I just couldn't believe the high-energy neutrinos, that we would actually see high-energy neutrinos from this event as well. This just seemed to be too much. And indeed, this was the one thing that subsequently went away with continued investigation. But everything else held up. So what was in my inbox when I went to check? What was the data that Paul had been looking at and that our colleagues around the world had seen the evening prior? So here is a series of time series for different instruments. So each column here represents a different measuring device, and the x-axis is time. If you can't read it, it's running from about -10 seconds to 6 seconds, and t equals 0 is when these 2 neutron stars coalesce. Let's, I guess, begin on the bottom with the LIGO data, which is taken from LIGO Livingston Observatory. This is a spectrogram. So you're looking at frequency on the y-axis running from 50 to 450 hertz or so, and time. And this track you see, which is visible easily to the naked eye, is a so-called chirp. This is the final moments of the 2 neutron stars as their orbit is decaying from the emission of gravitational waves. They're moving faster and faster, approaching speeds comparable to the speed of light. And when they finally merge and get close to the point where they touch, they're already kind of disappearing into the noise. So At higher frequencies, above a few hundred hertz, the LIGO sensitivity is dominated by photon shot noise, and we lose these neutron stars as they disappear into the static fuzz of high-frequency shot noise. So we don't actually really see them merge, but you do see them inspiraling inevitably toward each other, and the merger is essentially inferred. The signal-to-noise ratio on this is absolutely enormous. It's 32.4. This is the loudest event that was ever detected with gravitational waves, louder than our first event, 150914, which was remarkable for its loudness. And you didn't need any kind of fancy algorithm to see this. We spend a lot of time in gravitational wave astronomy creating algorithms to find events. And this one, you could have just been watching the data come in and pressed a button to say you saw it. It was unmistakable. If you compare that then above, there are 3 time series which correspond to photon counts per second for two satellites. The top 2 are the Fermi GBM satellite, and there are the 2 rows just correspond to different energy ranges for their gamma ray burst monitor. Top panel is 10 to 50 keV, and then below that is 50 to 300 keV. The third panel is the integral satellite, which is another gamma ray burst observing satellite. And for all 3 of these panels, the 2 Fermi bands and the integral band, you see data that are consistent with noise. And then 1.7 seconds after we infer these 2 neutron stars to have merged, we see a burst of gamma rays. And this is a short gamma ray burst. And I'll talk about exactly what that is physically. But this was a remarkable moment, the first ever detection of a binary neutron star, the first ever coincident measurement of a binary neutron star with a gamma ray burst, something that I didn't think would happen until 2021 or so. This set off an amazing chain of events. So you saw earlier the sky localization that we achieved for the black hole 170814. Here's how we were able to do with 170817. Here is the sky, and this little patch here, for which 5 degrees is about this size, is the area we were able to isolate the event to. And so we sent out a GCN notice to our electromagnetic astronomer partners all over the world. There are about 70 of them. And a race was on in order to identify the host galaxy that this event might have come from and to catch whether there might be a flash of light called a kilonova, which would be associated with this binary neutron star coalescence. And I'll mention that this localization region comes entirely from gravitational wave data alone, and that in addition to knowing where on the sky to look, we knew from the amplitude and duration of the gravitational wave signal that it was created from a neutron star binary about 40 megaparsecs away, give or take 10 megaparsecs. And so this limited the number of possible host galaxies that could be the home of this event, because we know it's about 30 to 50 megaparsecs away, and we know where in the sky to look. But still, there are quite a few galaxies, and so for the next hours, various astronomer teams from around the world tried to find the galaxy where this thing may have gone off. And the first discovery, the first team to announce that they had identified the counterpart for 170817 was the Swope team. And here's a beautiful pair of images showing you their discovery. On the left-hand side is the reference image that they used in order to see if anything new had appeared. This was taken with the Hubble telescope back in April. And it's just a picture of this fairly, if you're an astronomer, fairly well-known elliptical galaxy, NGC 493, which happened to be, if I go back a slide, in the middle of this allowed region that LIGO had sent out. And here it is before. And 11 hours after the neutron stars merged, Swope took this image. And the arrow is pointing to this thing that looks like a new star that's been created, but is in fact, it's a rapidly decaying glow of the kilonova associated with this binary merger. And a fascinating little side note, you could really have an entire talk just devoted to Swope, because it's an amazing human interest story. some of the biggest and most powerful telescopes in the world were engaged in this race to be the first to see the electromagnetic counterpart from 170817. But it turned out that the one that saw it first was a relatively small 1-meter telescope in Chile, which was operated by a young faculty hire and a ragtag band of graduate students and postdocs. So the little guys were first on the scene, and it's kind of a nice story. Once Swope identified the galaxy and told by GCN notice the rest of the electromagnetic observers to look at NGC 4993, everyone around the world was able to image this one galaxy and watch the kilonova. And I'm going to play you a movie now to show you what they saw. There are two images that you kind of have to watch simultaneously. So on the left-hand side is the photometry image. This is just showing you it's essentially a photograph of this galaxy. And if you look over here, a spot will appear, which is corresponding to the counterpart of 170817. Simultaneously, though, we're going to plot the spectral data, which is showing you the relative contributions from different wavelengths of light. So shorter wavelengths is bluer and higher energy photons, corresponding to hotter temperatures. And as you go toward longer wavelengths, this is colder, lower energy light. So initially, you won't see anything, and then the spot will appear. So it started. Boom, there it is. It's right here. You can see it's blue, but the light curve is, the spectral information is changing quickly, and it's fading. And look, this is getting redder. So I'm going to play it again for you in a second. But as we've got up to 9 days now, it's faded almost into the point where you can't see it anymore. And this movie ends at 11 days. So I'll play it again in just a second. But now that you've seen it once, as we rewatch this, look at what happens. We got the appearance. We have something that's initially very blue, and it rapidly decays. And as it decays, it's not just getting dimmer, but the spectral content's changing. It's becoming redder. And this is a really smoking gun signature for a kilonova. There's nothing else that behaves like this on this time scale. So here we are, 2 days. We have an appearance, 3, 4. It's reddening, 5, 6, 7, 8, 9. Now getting hard to see by the naked eye, until finally at 11 days it's starting to fade into the background. So what does that all mean? In order to get a very sort of cartoonish understanding of the astrophysics of a binary neutron star merger and a kilonova, we'll just take a look at this cartoon, a fairly famous cartoon. And I'll highlight that this cartoon is from a paper by Metzger and Berger, which goes back to 2011. These are not the only two authors to have worked on kilonova, but I want to highlight that some very bright astrophysicists were able to predict a lot of the features that we ultimately saw, which is pretty cool, back in 2011 and even earlier. OK, so here at the center of this cartoon is the central engine. We have some post-merger object, which Paul will tell us about, which is created when two neutron stars collide. And then there's a disk of material that is created when the two neutron stars merge. And this forms an accretion disk. The initial electromagnetic signature that we see is the gamma ray burst. And as far as we understand, the magnetic field that is associated with this remnant object gets wound up by the spin of this remnant, and that channels relativistic jets, which, and then the shock acceleration of these jets creates gamma rays, which can be observed about 1/10 of a second or a second after the merger, and indeed we had about 1.7 seconds later. The jet is highly beamed, so if you're looking too far away from the jet, you might miss the gamma ray burst, or it might be very faint. But what people have been very interested in terms of kilonova is not this gamma ray burst, but rather this ejecta. So the mass is ejected, in addition to the jets, mass is ejected in sort of two ways. One way is the tidal tails, and you can think of the tidal tails as you have these two neutron stars going around each other, and as they start to shred, material just gets flung out dynamically through the motion of these two neutron stars. And this contributes some of the material in the ejecta. But then also there's a separate component which comes from the disk wind. So in addition to the material that's flung out, the disk of accretion matter is very hot, and it sort of boils off matter which is added to the ejecta. The ejecta is basically a radioactive material, and through a process of neutron capture and beta decay, it heats up and radiates electromagnetic radiation. And the kilonova that you see is the radioactive decay of all of the heavy elements which are produced in this kilonova. And we think that the reason that it starts blue and becomes red is because of these two components. The bit that's ejected from the disk wind is thought to be relatively low opacity, and so the light is able to escape quickly, and you see it when it's very hot and blue, whereas the tidal tails involve a higher opacity material that's harder for the light to get out because lanthanides have been created. And so this is a redder, it cools down before you see this, and so you get a redder component. The light curves that I showed you in the spectrum that I showed you in the previous movie are just one piece of the cornucopia of electromagnetic information that was harvested from this event, which I think one could argue is maybe the best observed astronomical event in all time. So I won't go through this in gory detail, but this is just a list of various bands that you can observe this event in. We have gravitational waves on the top. We have positive detections of the initial gamma ray burst. Many days later, there was a confirmed detection in the X-ray. And these are telling you about either the jet or the central engine of the merger. In the UV, optical, and infrared bands, we have detections that come some number of hours later, although it's possible that if we'd been on the target earlier, maybe we would have seen this go back even earlier. And this, broadly speaking, is telling you about the kilonova from radioactive decay. And then finally, at the bottom, we have observations in the radio. There was a positive detection, including a measurement made by colleagues in Australia. And the radio observations are giving us information about the shock fronts from this event colliding with the interstellar medium, we think. From the gravitational wave data alone, we are able to say quite a bit about this system. And on this slide, I'll focus in particular on the masses of the objects. So how this works is that if you have very heavy compact objects like tens of mass black holes, they cause the gravitational waveform to be very short, and it exists in the band for just a small amount of time. But when the compact objects are relatively light, the system takes longer to merge. And so by comparing templates from numerical relativity with the data, we're able to reconstruct the possible ranges of mass. And because this waveform was so long, we know that this masses must be relatively low. And this is a posterior distribution plot. So the x-axis here is the mass of the heavier object in the system. And the y-axis is the mass of the secondary or the lighter object in the system. And ignore the red for a moment and just look at the blue. The blue is telling you that the masses of this system were somewhere here. So the heavier one was maybe up to 1.6 solar masses, and the lighter one maybe went down to a little bit less than 1.2. But from this, this is why we think that these are, among other reasons, why these are neutron stars, is because the masses are consistent with the neutron stars that we see in our Milky Way galaxy. And they're not even exotic neutron stars. These are kind of vanilla Milky Way neutron stars. OK, but what about the red? The red is telling you the same thing, but if you make a different assumption about how fast these neutron stars were rotating as they merged. So for the blue, we assumed that they were not rotating any faster than the fastest rotators in a binary neutron star system that we see from radio waves. But you could say, well, maybe that system is not typical of binary neutron stars in distant galaxies. Maybe these neutron stars were spinning close to breakup, so much, much faster than other neutron stars in binaries. And it certainly is fair to assume this. We don't think that binary neutron stars are spinning, that neutron stars and binaries spin so fast when they merge. But if you allow for this, then your constraints become much weaker. And the neutron star mass can go all the way up to 2.5, which would make it, for the primary, which would make this much larger than the, and as low as, I guess, 0.8 for the secondary, which would make these fairly exotic neutron stars. So now that we've gotten a little snapshot of what we saw with 170817, we can go back and put this discovery in the context of what we've seen so far with binary black holes. So here is a nice plot from the LSC of the masses of, in the so-called stellar graveyard of black holes and neutron stars. And the top plot, I don't know if you can tell the difference between the two different colors here, but there's meant to be purple circles and blue circles. The blue ones are kind of here, and the purple ones make like a smiley face, I guess, for the spider eyes. The light blue ones, these are black holes that are detected by LIGO. And these, for stellar mass black holes, these are the heaviest, the most massive black holes that we know about. They all come from LIGO. We have some detections with LIGO that are lower mass and are more typical of these black hole masses that we know about from X-ray astronomy that are the black holes in our own Milky Way galaxy. All right, but let's go and look down here at these yellow and orange circles. These yellow circles are the neutron star masses that we've been able to measure, not necessarily neutron stars in binaries, just neutron stars in our own Milky Way galaxy. And they tend to run between 1 and 2 solar masses. The error bars are not included on here. And the orange is showing you the best fit values for our neutron stars in our own galaxy, from 170817. And it appears that the two objects, as I indicated earlier, were sort of typical neutron stars, but the remnant object that they made is in this gap. And there's not really anything we know about that's like it.
Thank you, Eric. So this is the only part of the slideshow where Eric and I completely disagree. And so it's as good a time to any to take over. Just keep it there. So it's as good a time as any to take over because, Eric thinks this is one of the best plots that we produced, and I completely disagree with this. This is a plot that was produced by the LIGO Education and Public Outreach team, which is to say that it doesn't include those fun details like uncertainties, error bars, that all my first years who are here know, I harp on a lot about. But it's actually really important. So we have these two neutron stars, we think. We think they're neutron stars. Eric's done a good job of trying to convince you of this fact, but we're not too sure. So we have these two objects that merged, created another object of some given mass, and we have some handle on what that mass is, but we don't actually know what the remnant is. Is that a neutron star or is that a black hole? And if you just stare at this plot, then you would see that this other point over here looks exactly the same as that. So, aha, that's a neutron star, so I'm satisfied. But this is not right, because there is an error bar associated with this guy that is actually huge. Okay? And this is actually a really important point if you are interested in neutron star physics. And the reason it's an important point is that neutron stars actually have a maximum mass. And above that maximum mass, what they do is they collapse to a black hole. But we don't actually know what that maximum mass is because we don't understand how nuclear matter behaves at supranuclear densities. And these neutron stars are exactly that. They are bulk matter, so they have masses on the order of 1 to 2 solar masses. But the density is absolutely supranuclear. It's more dense than that inside the nucleus of an atom. And we simply don't know how matter behaves at those densities. So we can't actually say for certain whether this thing is a neutron star or a black hole. But we can try and understand that, and that's one thing I'm going to argue very shortly. But of course, there's another problem. And Eric's tried to argue that actually the progenitor, so the two things that merged, were actually neutron stars. And he's only really been able to do that by pointing at the masses. And it's absolutely true that we know of no black holes that have this kind of mass. But it doesn't mean that they don't exist. Now, I'm going to show you a complicated plot, and I'm going to walk you through it reasonably slowly. But this is a plot that actually says that we don't really know that these two things were either neutron stars or black holes. But it actually points a way to, in the future, we should be able to do this. We should be able to tell this information either with better sensitivity of our instrument or with just more of these mergers. So what you're looking at here is a parameter called lambda. This is what's called the tidal deformability. Okay? And you can see this is the tidal deformability for our more massive neutron star on the horizontal axis. And on the vertical axis is this tidal deformability parameter for our less massive object. And this tidal deformability is basically the ability for a neutron star or a star of any type to change its shape due to tidal forces. So if I think of an isolated neutron star and it's just sitting out there in the universe, then all other things being equal, this will be completely spherical. But now all of a sudden I take another neutron star and I put it in the vicinity of this first neutron star, and it means I have very strong tidal forces. And these tidal forces will try and make my first neutron star actually elongate. Okay? And the ability for that neutron star to elongate and to actually change is this tidal deformability parameter lambda. So, very loosely, the further out I go, the higher this tidal deformability, the more it is allowed to deform, the more sort of puffy it is. And the more this neutron star, or this star in general, can actually deform given the tidal forces around it. As I go towards zero, I get to the regime of black holes. Okay? So when this tidal deformability parameter is zero, all of a sudden I have this regime where the neutron star, or the star itself, is not allowed to deform. Okay? It's so compact and it's so rigid that it can't actually change its shape very much due to the tidal field. So what you can see here then, the colours on this plot, you can see that it's very dark blue in this regime and it gets lighter and lighter blue out here. And what this is actually pointing to is this is the region of this space that is most consistent with the data. So you can see here's a 50% contour interval, here's a 90% contour interval, which basically means that we're 90% confident that these two neutron stars sat somewhere in this tidal deformability space. Now it turns out that's not actually very constraining, and most models of neutron stars, most equations of state that nuclear physicists give us, are actually reasonably consistent with this. So just a couple of representative equations of state are plotted on here. It's probably difficult to see, but you can see the labels. There's an APR4, they're all given really weird names. APR4, SLY, MPA. These are all equations of state that are absolutely consistent with this observation. There are a couple of the more exotic equations of state. These are the sort of really puffy equations of state. They give you neutron stars that are really sort of fluffy, they have big radii, and these are inconsistent. And absolutely, from these observations, we can rule out exotic equations of state like this. But going in the other corner, if I look here at this 0, 0 point, there's actually no real good reason to say, just from a plot like this, that I can necessarily rule out that one of these objects wasn't a black hole. Just from the gravitational wave waveform data. Okay? So absolutely, it's a good argument that the masses, we don't know of any black holes that are only 1 or 2 solar masses. But just given the tidal effects, we can't definitively rule out that one of these objects wasn't a black hole. Of course, we can definitively say both of the objects weren't a black hole, given the amount of electromagnetic emission that we saw, and even the gamma ray burst. It's very difficult to create a gamma ray burst if you just have black holes, but we don't know that it wasn't just one of them. So is there any other evidence for this? Well, this is actually an interesting question. And what I'm going to do now is I'm going to show you a movie. And this is actually a beautiful numerical relativity simulation by a group in Trento in Italy. And what we're going to look at is we're going to look at the two neutron stars. Okay, and these have masses approximately in the middle of the posterior distribution for what we infer from the gravitational wave data. And if you can see it, hopefully there's a trace that's going to come up here. So if we play this movie, you see these two neutron stars are moving around each other. You can see this trace coming out. This is the gravitational wave signal. This is the inspiral phase. You can see we're just sort of milliseconds in. Then all of a sudden these two things merge. And you can actually see I've still got some kind of neutron star sitting here, and I'm still emitting a significant amount of gravitational waves. And then all of a sudden it collapsed to form a black hole. And you have, this is all of that matter. This is the torus, the accretion disk that Eric spoke about that sort of enabled that jet to be launched. But what I really want to focus on is what happened in the core here. This is just an example of a simulation where they've chosen one of those particular equations of state. And it happened to be that this neutron star, the two neutron stars collided, and then something survived for about 30 milliseconds before it collapsed to form a black hole. Now, had I had a different equation of state, something might have survived a lot longer, it might have survived a lot shorter, and it might have just, to be honest, you can actually get a neutron star that actually survives indefinitely, depending on the equation of state and the masses. So this is sort of, in some sense, a schematic of what happened. But the question then that's begged is, can we learn anything about this phase, either from gravitational wave observations or from electromagnetic observations? And the answer is actually yes. So Eric mentioned earlier that there's this kilonova emission. And he mentioned that this kilonova is this R process, this neutron capture that creates all of these heavy elements. And it actually turns out that the structure of that kilonova is actually imprinted on by that post-merger remnant object. And this is actually really neat. So here's a beautiful sort of schematic that's from another paper by Brian Metzger and Fernandez in 2014. And what this actually shows, again, is you've got this sort of disk area, you've got a lot of outflows and a lot of stuff going on, but they've actually got this HMNS, which stands for this hypermassive neutron star that's created in the core. And actually, because you have this neutron star that's created in the core, that is incredibly hot. It's on the order of 10 to the 11 Kelvin. And when something's so hot, it cools incredibly quickly. And it cools incredibly quickly through neutrino emission. So you get a huge amount of neutrinos that come out. Now, as Eric mentioned, that my initial text to him on the morning of the 18th of August said that there was a neutrino detection, and that since went away. Okay? You don't expect to be able to detect these neutrinos. So although the neutrino flux is absolutely huge, given their energies, you actually only expect to be able to detect them out to a few hundred kiloparsecs or maybe a megaparsec. Okay? So given that this event happened approximately 40 megaparsecs away, you don't actually expect to be able to detect these neutrinos. But they're there if this hypermassive neutron star lasts for any period of time. And the effect that they have is actually to change the color of this kilonova emission. So what happens is these neutrinos from the remnant raise the electron fraction of this disk wind that's coming out. And that actually changes the quantity of the lanthanides that you have and that are going on in your R process. So here's a beautiful plot from one of the observing teams of this latest event. And what they're actually showing here is, it's a little bit schematic. Again, there's no error bars, and I apologize for that. But it's showing brightness in terms of millions of suns, because that's not a unit we use at all. But anyway, it's showing brightness in terms of, as a function of the amount of time afterwards. This is very similar to that movie that Eric showed of the kilonova emission. And what you can see is it goes from this darkish blue, and then you get this absolutely beautiful blue bump before it starts decaying into that red and much weaker kilonova. And actually, this is beautiful evidence that there was this hypermassive neutron star that survived for on the order of hundreds of milliseconds before collapsing to a black hole. So it's amazing what kind of electromagnetic information you can get out of observations like this. And of course, then that begs the question. So we saw this in terms of the electromagnetic observation. Could we detect these gravitational waves? Right? You have this new neutron star that was created during the merger. It's highly deformed because it's rotating once every millisecond. Sorry, it's rotating 1,000 times every second. Once every millisecond was right. It's rotating with millisecond periods. It's rotating incredibly fast. It's emitting gravitational waves and spinning down. Can we detect those gravitational waves? Unfortunately, the answer is no. Here's a very complicated plot. But it basically tells you the answer to this, and it tells you the answer is no. So what we're looking at here is frequency. This is now the gravitational wave observation searching for this post-merger remnant. So this is gravitational wave frequency as a function of the spectral amplitude. Okay, so this is basically the strength of the gravitational wave signal. All of these different colored curves are the sensitivity curves of the different instruments. So this is actually a remarkable plot because we don't just have 2 or 3 instruments. We're not just now looking at the 2 LIGO instruments plus Virgo, but up at these very high frequencies on the order of kilohertz, we can actually use the GEO detector in Germany as well. And actually, at these high frequencies, the GEO detector in grey becomes very competitive with the Virgo detector, whereas at low frequencies, it's next to useless. And this is simply because it has much shorter arm lengths than the main detectors. But so what we're looking at here is, this is our search algorithm, and this is the upper limits that we could find for the gravitational wave signal from some kind of post-merger remnant. And what you need to do is you need to compare these red points, these red squares, with these empty squares, and these empty squares are the ones that you predict for a binary neutron star merger out at 40 megaparsecs, given various equations of state and various assumptions that you make about the physics. So while we expect that this hypermassive neutron star survived for a few hundred milliseconds, we're approximately an order of magnitude away from actually being able to detect this. Okay? Now, all of that is to say, an order of magnitude in this kind of science is actually not very much. So in the next couple of years, we're going to get the sensitivity down over here by about a factor of 3, which gets you really close. Okay? A factor of 3 in sensitivity plus improved algorithms, all of a sudden you start actually approaching this limit, and we start being able to make interesting statements. Of course, there's some evidence that this neutron star lasted for hundreds of milliseconds. One could actually argue that a neutron star lasted for even more, even hundreds of seconds, or even days or weeks, or even indefinitely. So we actually looked for gravitational waves from them as well. This is actually worse. We can do even worse on these for various reasons. And so here's a bunch of just sort of upper limits, which are sort of model dependent. And it turns out that we're sort of a reasonable way away from being able to actually detect anything here. But there's a lot of work going on in this space, and at Monash University in particular. So it's worth asking, just sort of changing steam a little bit, changing tack, what other things did we learn? We've given you sort of a little bit of a laundry list, but actually there's a whole lot of things that we've discovered about gravity and about various other aspects of astrophysics here that we haven't yet mentioned. So I'll just sort of give you a small laundry list of facts that are useful to take home to your families. So, because you're all going to, right? So one interesting one, for those of you that remember GW170817, that first gravitational wave event that we detected, approximately 30 solar mass black holes, that lasted in our band for approximately 8 cycles. And we could actually see those 2 black holes with the gravitational wave detectors for about 0.3 of a second. This thing, depending on how you count, it was above 30 hertz for approximately 60 seconds. And in fact, it was above 10 hertz, which is very close to what the limit of the detectors is, for approximately 1,000 seconds. And even just through this 60-second period, these 2 neutron stars orbited one another a few thousand times. Okay, so you have these solar mass objects going around each other incredibly fast. Okay, they're reaching velocities very close to the speed of light, approximately half the speed of light. We can measure actually the viewing angle, and this is sort of so the orientation of the binary, whether it's completely face on, whether it's slightly off axis, and this is actually very interesting for gamma ray burst physicists. This was the closest gamma ray burst that we've ever detected by approximately an order of magnitude, we think. But that's actually very dependent on this statement that we know what the viewing angle is. And so this is something where a lot of gamma ray burst astrophysicists are going to be asking a lot of questions about this event in particular and about all of the other GRBs that have been observed up until now. This thing had a host galaxy redshift of about 0.01. I'll get back to that point in just a second. A peak gravitational wave strain on the order of 10 to the minus 22. And again, to put that into context for you, our 4-kilometre long arms wobbled by about 1/10,000th the size of a proton. So you can take that one home to your parents. The amount of gravitational wave energy that was radiated was on the order of 3% of a solar mass, okay? 3/100ths of a solar mass. And actually, this is one that is incredibly interesting. The speed of light compared to the speed of gravity. So for all of you who have done either my third year or Eric's fourth year general relativity course, you'll know that Einstein tells us that the speed of gravity is c. It's the same as the speed of light. Okay? But we've had actually no really good experimental verification that the speed of gravitational waves is c and is the speed of light. Now, Eric showed a beautiful plot before that showed the gravitational waves arriving 1.7 seconds before the gamma ray burst. Now, I'm not going to try and tell you that this 1.7 seconds is because the gravitational waves were traveling at a different speed. Instead, that's the amount of time that it takes for the gamma ray burst to this jet to form, this jet to actually come out. But it does tell you something remarkable. This merger happened about 100 million light years from us, which is to say that the gravitational waves and the light traveled approximately 100 million light years, and the separation when they arrived was about 1.7 seconds. In other words, gravitational waves traveled at the same speed as the speed of light with absolutely remarkable accuracy, and it's quantified up here, about 3 × 10⁻13. Now, we've detected a lot of gravitational waves before in the last couple of years from binary black hole mergers, but because we've never had electromagnetic emission, we've never been able to make this comparison. We've never actually known when or where in the universe, to any reasonable accuracy, those gravitational waves were produced. So that's a nice little fact. This is just a little sort of schematic showing, actually, this is the first time we've really definitively been able to say that gamma ray bursts were caused by neutron star mergers. So we've been observing a lot of gamma ray bursts in the past. People have been talking for a number of years saying that these are definitely or should be from neutron star mergers, but we now actually finally have the smoking gun for this. And so what I'm showing here, this is actually the Vela satellite, which was the first satellite to detect gamma ray bursts way back in 1967 when it was supposed to be spying on the Soviets. One of the big take-home messages that you would have seen from a lot of press conferences is that this is where all of the gold in the universe gets produced, maybe, okay? And so this is the periodic table that you can get from Wikipedia. And it shows you where all of the elements in the universe get produced. This is the lanthanides that we've been talking about quite a bit. But what you can see here is everything in purple are the things that are believed to be produced in these binary neutron star mergers through this R process, nucleosynthesis. And so you can see it's actually mostly gold, plus a whole bunch of all these other heavier elements are actually produced in these binary neutron star mergers. And actually you can do this calculation and you can say, right, we've now detected a binary neutron star merger, so we know how often these things merge throughout the universe, and it's pretty often, okay? And we know approximately what the yields are for each of these heavy elements. It's a little bit model dependent, but we can do this kind of sum. And so we can take those merger rates, we can calculate how much yield we have per merger, and we can compare that with the amount of gold and the amount of all of these heavy elements in the universe, and we get pretty equal numbers, which is all to say that we can explain all of the gold in our solar system purely through the merger of neutron stars, which is a pretty cool thing to be able to do. So there's two more exciting bits of science which I need to really tell you about. It turns out we're actually doing cosmology. And this is actually a little bit of a surprise to some people, and this is actually something that I think is going to be very big in the next few years. So there was a beautiful paper by Bernie Schutz in 1986. And what it basically said is when you detect gravitational waves, you can actually, when you detect gravitational waves and you have an electromagnetic counterpart, you can start doing cosmology. And the reason is you can actually measure the luminosity distance to the source completely independently of the redshift. And so given that you know the redshift from the galaxy host, you actually know both the luminosity distance and the redshift independently, which means that you can form a Hubble diagram, which means you can do cosmology. And what's really cool about this is you're doing it absolutely independently of any kind of cosmic distance ladder. So when people do observations of supernovae, for example, they rely on the cosmic distance ladder of knowing how far away each of the rungs in their ladder is to actually determine the distance out to these supernova explosions. But we don't need to do that with gravitational wave cosmology. We can do it completely independently. So here are the results. You can see that they're not all that constraining. So what I'm showing here is the Hubble constant h naught in units of kilometers per second per megaparsec. Okay? And this is in blue, this blue trace is the posterior distribution that we can infer purely from this observation alone. The two vertical bars are our current state of the art, which are actually in slight conflict with each other. So the green one is observations of the cosmic microwave background and what we infer about Hubble constant from the cosmic microwave background. And the orange one is the Hubble constant that we infer from type 1a supernova. And you can see what's actually remarkable is that this completely independent way of doing cosmology is fully consistent with both of these measurements, which is really exciting. The more of these gravitational wave measurements that you make, the more this kind of spread out curve is going to peak upwards and actually going to be able to pinpoint the Hubble constant, among other things, and actually be able to do precision cosmology just using gravitational waves. So this is something to watch out for in the next couple of years. The other thing to watch out for in the next couple of years is something called the stochastic background. Next couple of years, maybe even earlier. So this is actually trying to understand if there are so many neutron stars merging in the universe at any given time, then there's a lot of them that are actually merging and the signal is appearing in our detector, but they're actually sub-threshold. Okay? And this detecting all of these things, it actually adds a noise floor into your detectors, and it's actually a noise floor that you can detect. And a lot of people in this room, in fact, this is sort of an effort that's being driven largely out of Monash. Letizia Samet, who's a postdoc here, is the chair of the stochastic working group. Eric Thrane's the former chair, and a lot of people, Rory Smith, working on this in great detail as well. But the hope is to actually be able to measure all of these sub-threshold events in your detector called the stochastic background. So this is a plot from a new paper that points out this fact. In red is the stochastic background from the binary neutron stars compared to the stochastic background from the binary black hole systems in green. Okay? And you can see that they're actually comparable. They've actually got comparable energy density in the universe is made up of this stochastic background. But what's really interesting is you can ask the following question. So this binary neutron star merger was in my band, it was in the detector for approximately 60 seconds, give or take. Well, how often do any neutron stars merge in the universe? And it turns out one binary neutron star merges approximately every 13 seconds somewhere in the universe. So if one's merging every 13 seconds in the universe and they spend on the order of 100 seconds in the band, it actually means that at any given point, at any given time, I have approximately 15 binary neutron star mergers going off in my gravitational wave band. And what this creates is this really low-level sort of humming sound in your detectors, which you simply can't get rid of. And this is actually binary neutron stars merging throughout the universe that we hope to detect. To put that number in context, you can ask the same question about your binary black holes, and it's on the order of they spend a lot less time in your band. And the fact that they spend a lot less time in your band means that there's a lot fewer of them in the band at any given time. And in fact, you have to wait a reasonable amount of time. There's on the order of 0.06 of these in your band at any given time. So these are very different types of signals. The binary black holes are these popcorn signals, we call them. So in other words, they stochastically, go off every now and then. Whereas this binary neutron star signal is actually this low humming background that's constantly there. Okay, I think I'm going to hand over back to Eric now, who's going to introduce our group.
I want to emphasize that we have a large group of people working in gravitational waves and LIGO science at Monash University, pictured here. And we even are joined today by Yuri Levin, who flew all the way back from Columbia just to hear this talk. Thank you, Yuri. I want to take a moment to recognize some of the contributions to this work that were carried out here at Monash. So the way that the discovery paper worked is that there was a core team of authors who were put in charge of taking in comments from the entire LSC. But then the entire LIGO Science Collaboration was able to comment on this and shape the paper. And I'm very proud that our senior members of our group, our PhD students, postdocs, and faculty, were very active in this process. And a number of our suggestions working with the paper writing team were incorporated into the paper to affect the presentation and the interpretation of the results. I want to call out that Letizia Samet was one of the co-leads for the stochastic companion paper, which is one of the 13 papers that LIGO is writing in conjunction with 170817, and that Paul is a co-lead on the post-merger remnant paper, which I'm proud to say was just voted for submission to AppJ Letters last night. This is a bit of a fun paper because the analysis uses Monash-developed search algorithms to look for waveforms designed by other people at Monash. I was a reviewer for two of the papers, so I'm the burst group review chair at the moment, and I was also a LIGO reviewer for the Hubble constant paper. And in this capacity, Monash was able to make a serious, to seriously contribute to the interpretation of the gamma ray burst jet, for example, and aspects of the Hubble constant paper. I want to especially thank Kendall Ackley, who maybe raise your hand if you're present. OK, in the back. So Kendall had an amazing task. She arrived at Monash for a new postdoctoral position and was only here for about a month, and then was asked to basically co-lead and write the Australian Osgrav electromagnetic paper. So just showed up for a new job and then had to organize electromagnetic observations from a number of telescopes across Australia and work on the interpretation of these with the kilonova model. And this is an extremely stressful job that involves political savviness and also some serious scientific chops. And this is like, a terrible thing to give to someone on their first day on the job. So thank you to Kendall for that. She did an amazing job. Colum was involved in some of the parameter estimation runs that were used in order to vet our understanding of some of the mass plots, for example, that we showed you. And last, I want to highlight the contributions of Rory Smith, who's a new faculty member at Monash University. The interpretation of this event and even things like the sky maps that went out rely on something called parameter estimation, which is cottage industry within gravitational wave astronomy that uses fancy Bayesian statistics in order to be able to very accurately measure things like masses and sky location. And it's a very hard mathematical problem because it involves jumping around in these high 13-dimensional spaces. Rory was a key member on a team of people that developed fast parameter estimation. And without their work, we would still be waiting now for the parameter estimation to finish so that we would know where this thing merged and what kind of masses it had, and we would be continuing to wait for probably months more. So at the recent LIGO meeting, LIGO Virgo meeting at CERN, there was a standing ovation for this team and their efforts, and I want to recognize this important contribution from Rory. I'm sure there were other things that I left out, and I apologize for having to go through this quickly. I'm going to kind of skip over this slide because I'd like to leave some time for questions. We're already over time, but I just want to highlight one item looking forward. There are obviously amazing new projects we have going and a lot of exciting things to talk about, but I want to just highlight Duncan Galloway and his team that Kendall just joined, which have this very exciting detector, which is just in the process of coming online, called GO2, which is going to be engaging in electromagnetic follow-up campaigns in the future. And now that we know that you can actually see these kilonova from binary neutron stars that LIGO sees, it's looking like a very a wise investment in this project and very exciting science that we have to look forward to with GO2. I'll end with just this cartoon, which is created by a colleague of ours, Nutsany, who just took up a position at ANU. And there was some context leading up to this, which I've cut off. But this is Ray Weiss, who's a Nobel laureate for the discovery of gravitational waves. And he's gone over to his chalkboard, and he has a checklist. He has a LIGO checklist. Black holes, check. Neutron stars, check. Neutron stars with an electromagnetic counterpart, check. So now we have to fill in the rest of these boxes. We have black hole with neutron star, supernova, pulsar, stochastic, and for Paul, we've added a post-merger remnant. I think with this, we're happy to take questions.
discovery, and thanks for the great talk. Could I just chase you up on neutrinos? So presumably you didn't see neutrinos because they're far away and the solid angle's small. Would you expect a stochastic neutrino background that ought to be visible at some level?
You're the Super K expert.
Yeah, so there is expected to be a cosmic neutrino background of, I think, about 2-3 MeV neutrinos. And the way to look for it, and these are probably from supernova primarily, not from binary neutron stars, although maybe you'll get some higher energy ones from that. But water Cherenkov detectors doped with gadolinium for capturing the neutrons that are created in that nuclear interaction are the way to go for that. In terms of neutrinos from a neutrino background from binary neutron stars, it's been a while since I've looked into that literature, but I'm not aware of efforts to look for that one.
Back of the envelope, I think you can say that the amount of neutrinos you get from a binary neutron star merger are similar to for a supernova, and there's many more supernova explosions in the universe than.
Energy regimes are similar, or are they?
I believe so.
11 MeV characteristic energy for a binary neutron star. I think we were from the remnant, and supernova neutrinos I think are a few MeV if I'm remembering correctly.
The signal to noise ratio was higher than anything we detected before, but the masses of the neutron stars were a lot lower than the black holes. So why is the signal to noise higher?
Yeah, okay, so for those up the back who didn't hear the question, it was basically that the signal to noise ratio was larger than anything we had detected before, but the masses was a lot less. So this is basically a distance argument to leading order. So the binary black holes that we're observing are hundreds of megaparsecs away, and we're sensitive to them at that distance simply because the strain amplitude is larger because they are so much more massive. And so the lower masses, you need them to be a lot closer. So these were 40 megaparsecs compared to GW170917, the first ever measurement that we had that was similar signal to noise ratio, slightly less. So that was 30 solar mass black holes, so a factor of 30 in mass, but a factor of 10 further away in distance. Ballpark. I've learned many times in my life not to argue with you, Yuri, but I'm going to argue with you anyway. So yes, you're absolutely right. This is a really strange GRB. And so what's being shown here is all of the short GRBs that we actually have good distance estimates to in orange compared to this GW170817. And you can see that it is absolutely 4 orders of magnitude brighter just in terms of energy output than any, dimmer. It's 4 orders of magnitude dimmer than any GRB that we've known about. But you'll notice that there's only on the order of 10 GRBs, short GRBs, for which we have accurate distance estimates to. And there's about another 40 or 50 for which we don't have galaxy associations. So I personally think that this is now going to be an interesting question of people going back and looking at those other short GRBs and asking the question, well, how many of them were actually significantly closer than what we initially perceived? But
yeah, so I'm happy to give you my honest answer, which is, as far as I know, it's not an extremely secure claim. It was remarkable to me that the blue-red kilonova predictions seem to fit the data very well, but I'm sure we'll see a flurry, and we are seeing a flurry of interpretation papers that will continue to debate this for some time.
Yeah, this is interesting. So the question for anyone who didn't hear was, do we understand the 1.7 second delay? I think there are a lot of possibilities, and it's reasonably easy to get a 1.7 second delay. This is the first time we've ever made such a measurement, but there's a lot of physics that goes on. So for example, we need the timescale for that jet to get launched, and then the jet to sort of shock so that we actually get these gamma ray emission coming out to us. That timescale is not known. It's fair to say that just you can calculate the velocity with which that ejector is coming out and just sort of ballpark estimates for how dense the environment is around there. And if you do this, then it should be less than 1.7 seconds. So there's possibly some other things going on. It could be that the jet is not getting created until this hypermassive neutron star collapses to form a black hole. So it's possible that the actual collapse of that the collapse of that hypermassive neutron star to form a black hole, if that happens a few hundred milliseconds after, then there's all of these extra delays. I think there's nothing definitive at the moment, but there's a lot to be learned from this event.
I can take that one. So the gamma ray burst was actually announced first. So the GBM detectors on Fermi and Integral sent out a notice before LIGO sent out a notice that they saw this. The timeline presents things that we showed you, presents things as they happen astrophysically, not as they were announced by humans. So the satellites had their initial email alert sent out, and then LIGO members were sitting in the control room and taking shifts around the world and saw this trigger, which was coincident with a gamma ray burst. But when we went back and examined the data, the gravitational waveform is clearly, visible well before the gamma ray burst. So this isn't exactly what I wanted to show, but there are some nice movies online that we could probably pull up immediately after the talk that show simulations. And the first thing you see are these tidal tails and this matter getting flung off. It kind of looks like spiral arms in a galaxy. And this is the initial ejecta. And this is what people focused on primarily for the source of the kilonova early on. But then if you look at the dynamics of the disk, and there are other movies that are representations of simulations that do this, then the disk kind of looks like, visually, like stuff is steaming off of it from is being kind of burned off. And so this is the disk-driven wind. And that latter one is thought to be in the standard blue-red model. That's the blue low-opacity stuff that gets ejected, whereas the tails are the high-opacity red component that comes in later and takes longer for the light to get out. So this actually answers that. So what happens? This is a screen cap of a movie, mid-movie. And what happens is you initially, this is basically like a representation of a periodic table with isotopes. And you initially generate some lump of stuff, concentrated here, and then it interacts with itself, and neutron capture goes this way, and beta decay goes this way, and you populate up to here and make all of this heavy elements. And then, but then these are all unstable. And so once you run out of neutrons, because this thing is expanded and cooled, then it decays back into this valley of stability. And the elements that are left over and that are stable have an imprint on them from the R process stuff that takes place here.